hope it's working. No. Too bad. Let me check the. That's working. All right. Any questions?
Second problem, please.
I don't know the question. I can bring up the second problem. Second problem.
Next up, you can remember. Yeah.
Do you still remember the question?
This is like the integral and x and y.
Okay.
Yeah. Yeah. It's a lot of time on that. That's when I forgot to finish it.
All right, anyway, we're going to do lots of double integrals today here. So today's topic is about surface area. You know, I have a graph. In Calculus 2, we know how to find the area of the surface of revolution. Okay, those are special ones located around a fixed line, so it can become just single integral. So you don't worry about it. But if you are given the graph, okay, so you have a piece of surface, right? And z equals f of x, y, and the question is over the domain D, okay? So the question is how to find the surface area, okay? How to find the surface area. Now, there are some, as a formula is given there, and trying to, the question is how does it derive the formula, okay? So the idea, I'm just giving a brief idea. So you divide this domain into many rectangles, okay? And I just want to find the corresponding piece on the top here to the rough estimate of the areas and add them together, and that gives you the surface area. So the idea is just to look at what I should say, and this is this is the x-axis, y-axis, yeah, and the change in x will be dx, the change in y will be dy. So the tiny bit area here at the bottom, it's going to be dA, right? dA is going to be dx, dy, something like that. Okay. If you just want to find the area of this domain, then just put the integral on dA, then double integral the area of D is going to be the double integral of dA, and then double integral is basically dA is just dx, dy. Okay, in something. So you can find the area. Now this domain is a flat, right? And then put to the space, it's curved surface becomes. So how do we do that? And this idea is very simple. You find the tangent line. The idea is that this will be the tangent line, that will be the other tangent line, and dA is going to be the area of this parallel. It's approximated by parallelogram. Okay, parallelogram. The tangent vector in that direction, in the x direction, and the tangent vector in the y direction. So those two vectors is going to be, it's called, yeah, u and the v. Okay, u is going to be 1, 0, and fx. Okay, at that particular point, that's u, and the v is going to be 0, 1, fy xy. Okay, and this way we how to calculate the the cross product. Okay, the cross product gives the normal vector. Do you remember that? Yeah, the cross product u cross v, okay, is going to be, let's calculate what is that. Okay, that is going to be I, j, k. The question is why this is both a tangent to the surface at the point xy f of xy. Okay, now I probably don't have time to explain that. This is a tangent vector to the surface, and the cross product is calculated by this formula, right? Then after expand it, you will get negative fy, negative fx, yeah. Okay, I, then j, negative yj, and then plus k. Okay, so in other words, the cross product will be something like that. Okay, will be something like that. This is a vector. Okay, it's not normal vector. Okay, now in geometry, if we have two vectors, the area of this parallelogram is going to be the length of the cross product. So the area of this area is going to be the length of the cross product. Okay. Yeah, it is the length of cross. It's actually is going to be the length of u times the length of v. If you know the angle theta here, it'll be sine theta. Okay. So clearly, if the length of u and the length of v times sine theta gives the area of the parallelogram. Okay, on the surface, let's go back to here. On the surface here, this is u and the v. Then, if you divide, yeah, this is the surface, right? And you just above the, you see, you partition the domain in the xy plane, but correspondingly you have like a net on the surface, okay? And then each piece is approximated by this parallelogram, okay? So imagine the surface area, we call it ds, okay? Is going to be the length, the area of this tiny parallelogram, which is uv, okay, the cross part. And now we see that ds, the small surface area is going to be this, okay? And not only that, actually it's a tangent vector, so I have to multiply it by dx dy, so dA, okay? Yeah, this is a du dx cross bar, because this is small one corresponding to tiny one in the domain D. So actually it's going to be like a u dx cross v dy, then take the norm, then dx dy taken out, you get dA. Okay. So this dA, and then the length of the cross product, clearly it's going to be fx squared plus fy squared plus 1 and dA. This is where it's come from. Okay. Now the surface is not necessarily be the surface of the graph. It's not necessary to be the graph of function. Then you can use the above formula to find the surface area element. Say dAs is called the surface area element. Okay. So the total surface area, I use this notation. The surface area is just the double integral of the surface. Yes. Okay. But this surface, this is the surface. Okay. S means the surface. And this, of course, you cannot evaluate, just like arc length, right? Remember, yeah, it's arc length. I probably don't want to put the where it is. Okay, it's very similar to the arc length function. Arc length like a L ds. Okay, now this is capital S. Okay, this is about surface. Then this can be translated, change it to the double integral over d when if you know the surface is given by the function. Okay, so this is how do we get the formula. Yeah, okay, it's very similar to the formula for the length of the curve. Yeah, for the length of the curve, I want to compare to the length of the curve. Okay, so you just have a curve. It don't have to be the graph of some function. Then the length of the curve is just the integral ds. What is s? S is arc length. Okay, s is arc length of this curve s. Okay, now since this is a graph of a function, okay, then ds is going to be just 1 plus, the f prime x square and dx. You see, very similar, right? Then you can use the interval. This is above the interval. It's similar to the d. Right now, just one dimensional. So that's the interval. So the length is going to be the integral of this function. Then now we move to the two-dimensional surface, and of course it's more complicated, and it's very similar, right? Partial derivatives of f and partial derivatives, yeah, of f with respect to y and square. Okay, and here's one, right? Because you have two variables, that's why you have a f partial derivative with respect to x square, and plus partial derivative y with respect partial derivative f with respect to y square. Okay, so those two formulas are very similar. And you imagine you can go high dimensional. Yeah, you can start a surface in the 100-dimensional space. Okay, if it's graph of some function in 100 variables or 99 variables, then you have the similar formula. Okay, so that's all about the surface formula. Yeah, the idea to get this formula is in this picture. Okay, we just draw the yeah, we partition the domain into rectangles. Okay, and about rectangles, you have a piece of surface which can be approximated by a parallelogram. Okay, the side, yeah, determined by the two tangent vectors to the surface. Okay, and of course the tangent vector could be very long, but it have to multiply by dx. So let me talk about why this is a tangent vector. So if we have a surface, right, here a sphere, right? So how do you describe the curve just above this strict line? Okay, this is a line when x is y is fixed, x changes, right? So you get a corresponding curve. So tangent vector to that curve is just the derivative of that curve, right? Yeah. So if here is if this is x is just t, y is fixed, for example, right? So the corresponding curve will be on the surface will be as a graph, right? It's going to be t. Yeah, this is a graph y 0 and f of t y 0, right? Because this is on the graph. So if I'm going to use that's fine, yeah. So so at the point, yeah, so this is going to be the tangent effect, right? Is tangent to the curve on the surface. Of course, it's tangent to the surface. Okay, so what is that? That is just 1, right? Derivative to 0. This is where it's come from. And then partial derivative of t, y, right? Okay, so that's the reason this is a tangent vector to that particular point. Okay, and this is a, yeah, so this is a tangent to the surface. Okay, that is a point, yeah, which is a point on the surface. Okay, so it's t0, y0, f prime, f t0, and t naught, y naught. Okay, all right. So I just trying to explain to you why this become a tangent vector to the surface, because tangent vector to the corresponding curve on the surface. Okay, that curve is above this strict line, parallel to the x-axis. Okay. Yes. All right. Now let's do some exercise from the book. Most of the time, I'm just want to set up an integral, okay, to even iterated integral to evaluate the surface area. Okay, find the area of the surface. The first problem is, this is the surface is given by 6x plus 4y plus 2z equals 1. That lines inside the cylinder. Okay, x squared plus y squared equals 25. All right, so we want to study this. We want to figure out the surface there. So this is a cylinder. Yeah, it's better to draw the graph. Okay, now it's harder to draw the graph for this plane. This is a plane, but the normal vector to this plane pointed to that direction. So it looks like that when it cuts through the, yeah, it looks like that, right? This is a plane. Yeah, just sketch it, okay? Yeah, just cut it through. Yeah. So the normal vector is going to be 6, 4, 2. Okay, they're all positive components. Okay. So first of all, you have to view the plane as a function, as a graph of function. So z equals 1 minus z equals, you have to divide by 2. So equals 4 minus 4x minus 4y divided by 2. Okay. So this is a graph of that function. So this is a f of x, y. Okay. Yeah. Next, we have to find out ds, the surface area element. Okay. The surface area element, you have to find the partial derivative of this, right? It is going to be negative. Yeah, this is a constant here. So it's a 1/2 minus 3 minus 2y. So it's negative 3. Fy x y is going to be negative 2. So it's constant. Great. Okay. So ds is going to be, and it's dA. Okay, you can dx dy. Okay, dA is just dxy. All right, so it is going to be 3 squared plus 2 squared plus 1. It's 9 plus, it's square 14 dA. It's constant. Yeah, it's constant, then it's easy. Now, the domain D, let's write down the domain D. The domain D is inside this disk, okay? Right? Because it's a cylinder, inside the cylinder, lines inside cylinder. So cylinder has a radius of 5, so that's what this domain. So the surface area, oops, the surface area, okay, it's called area of a surface, okay? It's going to be the double integral of 14 dA, square 14 dA, okay? This is actually the ds part, okay? The capital S, the surface area element, add them together. So you only get the double integral of dA, which is just the area. So it's very simple now. It's just the area of D. Okay. So area of D has a radius. This is a disk of the radius 5. So it's pi r square. R square is 25, right? Yeah. So this will be the answer. Okay. Yeah. Let's do the next problem. The surface is given by, yes. It's just the area of the domain. No. Okay. This double integral dA, right? And of course you can evaluate integral, no problem. But since we understand this is going to be the area of the domain D, because the integral of 1 gives you the area of the domain D. So we already know that the domain, this D is a disk with a radius 5. So that's why it's pi r square. That's why I write down pi r square. You don't need to waste time to evaluate this double integral. You can use, if it's double integral of a triangle, it's integral of 1 over a triangle, just find the area of the triangle, right? You don't need to evaluate this double integral in this case. Use the geometric meaning of this double integral to get the value. Okay, so this I just say from here to here, as long as you say this is going to be the area of the D, and I have another formula for the area of the D, so I just write down. Okay, yeah. But in the next problem, okay, I end up with double integral of a domain D, but this is a function which is not constant, so I'm not able to. I have to evaluate the double integral. Okay, so this is a problem number 4 from the book. As the surface is given by 2y plus 4z minus x squared equals 5, and that lies above the triangle with vertices 0, 0, 2, 0, 2, and 4. Okay, it's hard to draw the graph, right, because the xy plane is horizontal here. Right, so this is a point 2, 0, and 0, and the 2 and the 0 is here, 2 and the 4 somewhere here. Okay, so this is a triangle D. All right, right. Yeah, it's parallel to the y-axis. I did not draw the parallel. I needed to redraw it. It still doesn't work. That's fine. All right. So this is the graph is supposed to be above the xy plane. Okay. So how does this is going to be z, right? Divide by 4, and the 5 plus x squared minus 2y. Right. It's pretty strange function right now. I just want to make sure this is indeed above the plane. It's not easy to see that. Maybe some portion below the problem tells you that it is above the plane. Okay, you can check that whether z is always positive. Look at the end point for when x equals 2, y equals 4. Let's double check. The z is going to be 5 plus 4 minus 4 times 8 is 8. So, okay, almost make it. It's going to be quarter, it's positive, okay? When x equals 2, y 0, definitely it's positive. When x equals y 0, it's positive. So I think it's going to be above the plane. It's harder to draw it. Anyway, it's a surface. Pieces like that, okay? So we want to, this is a point 5 over 4, and this is a height when x equals 2. No, it's not a perfect graph, okay? We're supposed to be high at this point. But anyway, so this is a picture and a sketch of the graph, and we want to find the surface area element, okay? So the function here, f of x, y, is going to be 5 over 4 plus quarter of x squared minus 1/2 y. So let's find the derivative. Right, that's going to be 1/2 of x. Okay, f of y. It is going to be just negative 1/2. Okay. So my ds is going to be this square plus 1 and the dA. Okay, dA is just dx dy. Right? dA is the area element in domain D. All right, so now squared. So you will get a quarter of x squared, and this is going to be 5 over 4 and d. So the surface area is going to be the double integral of this triangle and integral of this function. Okay. So the triangle, let's draw the triangle. Right now, focus on triangle. So it's much easier to draw the triangle. The triangle looks like that. This axis is this y-axis. Here's 0 and 0, right? One of the point is going to be 2 and 0. Another one is 2 and 4. It's very high here. So this is a triangle, right? How do you evaluate this area, double integral over this triangle? You have to change it to the iterated integral. I'm going to do both, okay? So I draw these two pictures, the same picture, but I'm going to get two different iterated integrals, okay? So here's 2, and this is a, this is going to be 2 and 4, okay? First, I'm going to use a vertical line segment to write down the iterated integral. So the surface area is going to, first of all, x is between 0 and 2, so dx, right? For each fixed x, what is the equation for this line? equation for this line is going to be y equals 2x. Okay, y equals 2x. The slope is 2. Yeah, slope is 2. Yeah, the slope is 2, so y equals 2x, or x equals half of y. All right, so for fixed x, the y value changes inside this triangle from 0 to 2x. Okay. And this is one of the, yeah, I think we can, I like this one because I can evaluate the integral right now. This function right now is independent y, so I can view it as constant. So you get 2x of this, right? 2x times this. Then you can use the end substitution to solve the problem. So you let u to be a quarter. Okay? Then what happens? Du equals half of x dx. Okay? So x times dx is going to be 2 times du. Okay? We also have to figure out what is the lower bound and the upper bound, right? So this is going to be when x equals 0, the u value is a 5/4. When x equals 2, I think it's 2 is 4. 4 plus it's 9/4, right? And x times dx is 2 du, so it's 4, right? And then u to the 1/2 du, okay? Then you find the entire derivative of this and evaluate at the two endpoints. Okay. And then you get answer. 9/4 to the 3/2 and the 5/4 to the 3/2. You can simplify the first term a little bit, but you cannot simplify the second term. It involves square root 5. Yeah, I lived here. Okay, so now, how about use a different order of the iterated integrals, right? You can still do that. Okay, the function is going to be, yeah. So it's y is from 0 to 4. Okay, the area, the surface area, right? You know, it's still the double integral. Let's recall the double integral. Okay. Right? I want to express it the iterated integral. Maybe I'm not going to evaluate it. So this time I'm going to choose an arbitrary value y. Right? This line is going to be x equals half of y. Okay? Y equals 2x. So now you get horizontal line. Right? So y starts from 0 to 4. But for each fixed y, x start from half of y and the stop at 2. If you work on this, it's very difficult because you have to evaluate this integral involves radical. Okay? Then, yeah, this integral is difficult, right? You have to use a maybe trigonometric substitution, or you look at the table on the back side of the book. Okay, you can find, and it's almost impossible. Yeah, it takes much longer time, so we don't use this iterate. So sometimes you have to, if one iterated integral does not work, and you switch to the other one. Okay, yeah. In this case, of course, you probably automatically use the first iterated integral. But in some cases, the second iterated integral is easier to evaluate. Yeah, and for example, the function inside the function depends on y variable, right? Then it's better to use this iterated integral instead of another way. Right, so at least you have to express it as iterated integral. If it does not work, then try a different one. Right? This is how do we evaluate, how do we find the area? So now let's try another problem, number 8. Let's keep it on. So the surface is given by 2/3 x to the 3/2 plus y to the 3/2, and x is between 0 and 1, y is between 0 and 1. Right? All right. So the function is given, the domain is given. The domain is nice. Okay. All you have to do is to set up the integral for the surface area. Right now, I'm not. Yeah, set up an integral for the area of the surface. Okay. Yeah, those surfaces are very special surface, just a graph. Because that some surfaces can be not necessarily a graph of one single function, like a sphere cannot be a function for one. Yeah, cannot be the graph of one single function. Okay. You have to use two functions to describe the surface. All right, so let's maybe we can find the surface area of a sphere here. Okay. At least we should set up the integral, right? Okay, let's do this. Okay. So first of all, yeah, let's call it f x y, right? F prime x y is going to be the integral of, this is going to be just half of that, right? Then fy x is y to the 1/2. So ds is going to be the square root of this and here, right? So in other words, it's just equal to x plus y plus 1 here. Okay, good. So the surface area is just the double integral of ds, right? But then this can change it to the integral of a d, the double integral of d with respect to x and y, right? So our d is just the unit square, right? So this is a d. 1 and 1, x-axis, right? So it doesn't matter which one you can use, right? You can use 0 to 1, 0 to 1, x plus y plus 1 dy, or dx, doesn't matter, right? The question is, how do you evaluate this integral, right? I think it's easy to evaluate with respect to y. The antiderivative of that function, because y is a variable, x plus 1 is constant. So it's going to be 2/3 x plus y plus 1 to the 3/2. Evaluate the 2 endpoints and dx. And this is with respect to y, right? Yeah, when you differentiate with respect to y, you get square root of x plus y plus 1, right? So when you plug 1 for y, I get x plus 2. When you plug 1 for 0 for y, you get x plus 1. But it's okay. You still can easily find the antiderivative of each of this function. How? Right? 2 over 3 taken out, right? The antiderivative, first one is going to be 2 over 5. Okay? When you differentiate, 2 over 5 cancel out. Minus 2 over 5, x plus 1, 2 over 5. Okay? Not too bad. Okay, then you plug 1 for x, then you get the value. Let me take the constant out. Yeah, it's going to be 4 over 15. And when x equals 1 is 3 minus 2. And that's the first part. Minus 1 to 0. When it's 0. You get this. But you may be able to simplify. I stop it here because I don't think it's making it simpler. So for your answer, at least you have to express like that. In some books, they wanted to express a number as simple as possible, like 2 to the 5th. How do you express it? 2 to the 5th is 2 square plus 1/2, right? So it's going to be 2 square, 2 to the 1/2. You're supposed to express in that form. Okay? And similarly, 3 to the 5 or 2 is going to be 3 square plus 9 square 3. Okay? So the above answer will be 9 square 3 minus twice of that. So it's going to be 8 square 2 and plus 1. Some more friendly expression. Right? We are familiar with square root of square root 2. Okay, that's that looks better maybe. Right. Yeah, for this section, you at least should know what is the meaning of ds here. Represents what? Okay. So yeah, we'll talk about this at the end. Okay. I probably have to. Yeah, let's do one more exercise. Number 10. Right. The surface is a part of the sphere. X squared plus y squared plus z squared equals 4. That lies above the plane. Okay, z equals 1. If you're given the integral, double integral, that's okay. The difficult part is to draw the graph always. Like that, this one is okay, and it's a sphere. It's easy to draw. But there are some other graphs you have to quickly sketch it. Okay, then you set up the integral. So here, how do you do that? That's pretty standard, right? You draw the sphere. Right? You draw the sphere. Right? This is a typical way to draw the sphere. Right? Otherwise, it looks like circle. You have to put another one. Equator, yeah. You have to, then it looks like a sphere. Okay, what is behind should be dot. You know, that's dot. Yeah, don't draw the solid curve, which is if it's not visible. Yeah, to you. Okay, then a plane. How do you draw the plane? This radius is 2, right? The plane is here, somewhere here. So this is the way you draw the plane. Okay, equal plus, right? Yeah. I'm not good about that, but that's what I learned from my math teachers. Okay, but it's better you take one course, architecture. You know, this is it's pretty helpful here. All the kids in the school maybe have some courses called drawing courses. Sometimes we ask the teachers, say, can you teach our kids something like how to draw the sphere, how to draw a plane, 3D pictures? Yeah, instead of like animals, Yeah, that training is very useful. I don't know whether you learned that. I see some students have a difficulty draw the sphere even, right? When I was grading their quizzes or check the home exams. Yeah. Some students can draw a very perfect picture. So you see, this is a cross section, right? So there's a circle around that. And behind, if it's invisible, you put dots, okay? All right, so now this looks like this plane. It's not perfect, but it's, at least you can see that. Okay, so we are talking about this portion of the surface. Okay, the question, how do you set up, right? I think when z equals 1, I want to find out the equation for xy. So when z equals 1, so x squared plus y squared plus 1 squared equals 4. So x squared plus y squared equals 3. So this is above a disk. So the domain D, this is a graph above the disk was a radius, was a radius square 3. Okay. So my D is going to be x and y. X squared plus y squared is less than equal to 3. Okay. That's a D. And this is a graph, z equals the function. That is going to be square root of 4 minus x squared minus y squared. Right? So the surface, this portion of the surface is graph of this function above that D. Okay, clear? Then, yeah. Then this D should be a little bit larger, right? Yeah, this is a D. Right? That's the domain D. Okay. So this is my function fxy. First one, yeah. First one, maybe you write down the formula for the surface area. It's double integral ds. This double integral be the double integral over d, and that is going to be f prime x squared. So you write down the formula so you know what I can do next to y. What's the motivation to find the partial derivative? Because I have to figure out the square root of x, that's this function, right? All right, so find the partial derivative with respect to x. Then this is quadratic function. This is the square root function. Actually, it's going to be, then it's 2x, so x to cancel out. Can you see that? Why I got, yes. So the function f is going to be 4 minus x squared minus y squared to the 1/2. So when you differentiate, you take 1/2 down, then you get 1/2 minus 1 is negative 1/2, so you get square root in the denominator. Then you differentiate with respect to x, where the inside is negative 2x. Okay, so you get this. Then you get the y. Okay, now then let's add them together. So I get x squared. Then I get y squared. I get 1. Okay, so combine them. Yeah, the numerator will be canceled out. Here's x squared plus y squared. Then 4 minus x squared minus y squared. Cancel out, cancel out, cancel out, cancel out. Yeah, it's not too bad. Finally, the surface area is going to be the double integral and the square root of 4 over 4 minus x squared minus y squared here. All right, so how do we evaluate this integral? The best way to evaluate this integral is use the polar coordinates. Okay, you still have to transfer, kind of substitution. We call it polar substitution, whatever. Okay, so this is a double integral of a disk, right? And x squared plus y squared is less than or equal to 3. But this is a D. So we have a double integral over this domain D. The domain D is a circle, is disk. Even you want to use the iterated integral, be very complicated, right? Yeah, iterated integral. I'm not sure it works. Okay, iterated integral. If you really want to write down the iterated integral, you can let, you can let x to be between negative square 3, positive square 3, arbitrary x. Then you have to get the y value for those two endpoints, right? The y value. Okay, I write down the iterated integral, one of theirs. But as you see that for each x, I have to figure out the y value, positive, negative, right? How do I get the y value? Negative 3 minus x squared, and then positive square root of 3 minus x squared. Then I don't need to put the 4 there, just 2, okay? 2 squared 4 minus x squared minus y squared dy. I don't think you can evaluate this integral. It's extremely complicated. So, but you can express it. If I ask you to express it as the iterated integral, that's the answer, okay? But you don't need to evaluate it. Okay, so we give up. What I'm going to do is I use the polar, we call the polar map, okay? So polar map defined by this, I equals cosine theta, y equals r sine theta, right? To describe the points in the disk, how do you do that? You take arbitrary point here, right? Here's the angle theta. So theta should be between 0 and 2 pi. R is between 0 and square root 3. Okay, this is the R. That's a C. This rectangle is mapped to the disk. It's kind of surprised, yeah. But you have to stretch it. And there's only one area that I think a 2 pi, this line and those two lines will map to the same piece here. Okay, so you just collapse this side, r equals 0, collapse this side, vertical side on the y-axis, collapse to 1 point, then you open then open the other side, closed up. Okay, so that's the kind of, imagine this is a map. Okay, so anyway, it's good, and then the integral can be translated. So x squared plus y squared equals r squared. Okay, that's good. So this double integral, right, is going to be the integral of a d bar. Okay, double integral d bar, and 2 over square root 4 minus r squared, right? And I also have r here and dA bar. Okay, yeah, this is r coming from the Jacobi of this map. Okay, this is already given. Okay, don't miss that part. Then you can do the iterated integral. You can say it's integral from 0 to square root 3. That's dr. Then integral from 0 to pi is 2r 4 minus r squared d theta. But it's nothing to do with theta here. So you take take 2 pi out. Okay, now you can evaluate this integral. Use substitution. Okay. Let u to be 4 minus r squared. So du equals negative 2r dr. Great. Okay. When I equals 0, I get a 4. When I equals square root 3, I get a 1. Okay. That's a u to the 1/2. 2r dr is negative du. Okay. And then you switch the order. Okay. Then you find the entire derivative of this function, the u to the 1/2. I think twice of that. Yeah. And evaluate the endpoints. Oh, that is going to be 4 pi. It's funny. 4 pi. What is the surface area of the upper semicircle? Okay. What is the surface area of the semicircle? This top. The surface area of the whole upper semicircle is 4 pi r squared divided by 2. So 4 pi r squared divided by 2. Okay, and it's going to be I is going to be 2, right? So it's going to be 8 pi. Okay, this is the area of the upper hemisphere. Now this portion we got is 4 pi. Right? This has a radius square root 3. Right? So it tells us if you cut over there, you get half of the area of the upper hemisphere. Okay, right? Yeah, so you can precisely find the location in the middle. See, this is you see, this should be true in general. You know, here's a 2, right? So this is a z is equal 1. Equals 1 is between the middle point between 0 and 2, right? So now you imagine, give us a sphere, okay? If you slide them into several 4 pieces, right? You know, the up half, right? For example, if you cut the watermelons around the watermelon, right? First, you cut in half, okay? You know that if the radius is, fixed radius, right? Then you get half area, right? Then the other one, if you cut if you measure it's the half of the radius, right? You cut through, you get 2 pieces. Now you can tell the surface area of those 2 pieces are equal. Yeah, okay? We did not know that before, now we did it, okay? So if you, yeah, if you cut this way, but the volume will be different, of course. The volume will be different. The volume is the bottom part is larger, right? But surface area is the same surface area, right? Yeah. Yeah, geometry is quite interesting, and about mapping. Right now, we just only in the book they try not talking about the mapping. Map the one domain onto another domain. It's harder to imagine. Yeah, but if you make a word map, okay, if you take my class called Math 462, there was about mapping. So how do you draw the word map, right? The typical way is to cut the earth into many pieces, stretch the north side and south side, and then you put down the wall, right? That's a typical way. The problem is the Russians looks too large. Actually, it's not that large. So you have to stretch the north side. So sometimes, wow, so big. Actually, it's not that big. It's a little stretched. Okay. Another map actually is nice, but not popular. I don't know why. You can map the sphere to a cylinder. And it preserves the area, but does not preserve the shape of the land. Okay, it still stretch a little bit, but does not change the area. That's a good part because we're talking about the land or the area of the land. Now right? The size doesn't matter in the longer, short, probably. When we say, is this country is larger than another country, we're talking about the area. We're not talking about like Chile, right? Chile, right? It's very low, right? It doesn't have that much land, you know. So like Vietnam, you know, that's from source, yeah, from China to all the way to, it's very long, okay? But Vietnam does not have that much area. So this kind of map is nice. It tells you exactly the same area, but I haven't seen any wood map like that. Okay, but it's more. But you can make it. It's called cylindrical map, and you can fold it. You can even cut one line. Depends on where you don't like it. If you don't like this area, just cut through and open it. It's wood map. Okay, if you want to put the United States in the center, just cut the other side and open it. It's a still rectangular map. Then all the countries, that preserve the area proportionally. That's in geometry. It's we can do lots of things. Without geometry, with this, we have to study more advanced geometry in order to understand those kind of pictures. We don't have a GPS. Honestly, some students ask me, beyond the calculus, what we should learn? Well, you will see that, it's more complicated, yeah, these things. We should learn, we can learn lots of things, okay? Especially if you're mechanical engineering, and if your major is flow mechanics, okay? If it's flow mechanics, it requires more mathematics than you imagine, okay? If you want to do very well in the area, you should get a master's degree in geometry and PDEs before you get into that field, okay? So interdisciplinary programs, I think, some good, sometimes good. Some students originally study chemistry and switch to biology, okay? Get a bachelor degree in chemistry and switch to biology, get a master's degree or PhD in biology, then those students usually do better than those just only in biology, because their knowledge, chemistry is quite, related to biology. Okay, so it's the same story here. We have many professors on campus. I look at the background; they're doing very well, and I find out the background is a surprise to you. Like the chair of the computer science department, and first of all, he earned a master's degree in geometry. This kind of things. Okay, pure geometry from math department. And he went to University of Colorado to get a PhD in computer science. Yeah, that's what makes him do research easily in imaging process. He worked closely with doctors. Yeah, the imaging process, this requires lots of geometry. And another example, I look at the chair of the electronic engineering department. Okay, and I found that he didn't have a PhD in electronic engineering. He got a PhD in mathematics. Right. I just randomly checked that, for fun. That's what I found out. So that indicates, you study engineering right now, you switch to medical science, you probably can do that. If you become doctors, probably you can easily work with engineering people, right? Design some new medical devices, for example. Suppose, you get a bachelor degree or master's degree in engineering, and you say, oh, I'm good. I want to go to medical school and become a doctor, right? And you find out the other person can easily work with the engineers than other doctors. They have trouble to communicate with scientists, honestly. Many of them, not all of them, okay? So only those has a strong background in engineering and science that can talk to scientists and develop new technology in medical science, okay? But I talked too much, and finally, I just want to emphasize how do I get the surface area. Let me talk about this. I just draw one small piece here, D. Okay, this is a domain D, right? The special, This is a dx, that's a dy, and how the surface looks like. Here's a surface, okay? The corresponding piece is here. Okay, and that piece, the area of that piece is approximate by, first of all, this tangent vector. Now, this tangent vector is going to be, the length of this tangent vector actually is going to be a negative fx 0, I think 1, and then dx, because it depends on how long the dot mark. And that piece is going to be 0, negative y, and z, I think. Yes. Okay. So this and the dy. Okay, depends on how long this. This is just above that piece. Okay. So you want to estimate the area. Area is approximated by this parallelogram. Okay. All right. So the area ds is going to be actually this is let's call it the yeah. So the cross product gives you this is a v, okay, for the simplicity, and then it's going to be u v, okay, and the dy and the dx. So dy dx, okay. So this is d is going to be dy dx. So this is going to be the area of this parallelogram, which is a good approximation of that surface, that piece of surface. Okay, so when here dx dy is so tiny, so add them together, the surface area is, that's why just add them together, then you get this. Okay, so this is nothing but we already did the calculation. The cross, you can do the cross product. Okay, so dx. That's why you get double integral. Yeah, let me emphasize it. Okay, so this is the idea. You know, to understand the formula. Okay, why do we have that piece? Okay, the idea is that you find the two tangent lines to the two curves just above the two edges of the rectangle. Okay, and then we take it, we find the tangent vector. If this is a graph of function, then you look at the cross product, and then the cross product gives you the area of this parallelogram. But the area of parallelogram is closely attached to the surface. If the surface doesn't change too much, it's almost the area of that surface. But here, dx, dy are all very tiny. So if you add them together, millions of these pieces together, and you find out, if you take a limit, this is going to be that's the value, exact surface area. Okay, so that's what we are. It's just a rough idea about how to get a surface area. That's it. So I have to finish cut to here, and see you.